Hello. Today we are going to talk about the basics of probability. It's going to be kind of maybe repetition for some of you who have seen some of the basics of probability in high school. But please note that it's going to be a more structured, a more mathematical treatment, somewhat mathematical treatment of probability. So it's going to be the purposes, as I'm going to be emphasizing again and again, is to replace your understanding of some formulation instead of your heuristics to solve probabilistic questions. So let's see what we are going to do and start with the probability. All right. So first I have to introduce a couple of nomenclature, I may say. The first one is the concept of random experiment. All right. So there is a term random here just before experiment. So what's the difference between a random experiment and a typical experiment? Actually, we can in somewhat say that almost all of the experiments are random experiments. So fundamentally, as a definition, an experiment that can result in different outcomes, even though it's repeated in the same manner, is a random experiment. Now, theoretically, it may be possible to repeat an experiment in exactly the same manner. But when it comes to practical terms, it's almost impossible. So you may say that, how is this definition satisfied? It's repeated in the same manner. We may say that in the same manner within the scope or within the resolution of the experiment. What do I mean by that? If, for instance, you toss a coin and you try to do it in identically the same manner, of course, it's not going to be, if you are interested, if you go into minute details, like the angle with which you throw the coin and the force you apply, there are going to be probably some differences, some fluctuations. But within the scope of the experiment, approximately you can say that the same experiment is repeated a number of times, and each time you do, actually you may get a different result. Actually it's going to be head or tails, but you do not get a deterministic result. So these kind of experiments are random experiments. So in a way, since in real life we cannot it's impossible for us to control all the aspects of an experiment, there are going to be always minor or major differences, however you try. So there are going to be maybe some differences, and due to that, almost all the experiments in real life are actually random experiments. So another typical example, you randomly chose a person and ask whether he speaks or she speaks English or not. The answer may be yes or no. It's not a single answer. It's not a single response, though. So therefore, although you believe that you achieved the experiment in identical way, note that it's not going to be identical. The person you choose is different, but that's because of the nature of the experiment. There are always going to be some minor changes. So it's that kind of an experiment, a random experiment. So this is the first term that we need to learn. The second term that we need to learn is sample space. Now, in a random experiment, we are still talking about random experiment. The set of all possible outcomes is called a sample space. So for the previous example, for instance, for this example, the person that we choose whether he or she speaks English or not, the possible answers, the possible outcomes are yes or no. So therefore, the sample space, we are going to call it S, is going to be equal to yes, Y, and N. So two elements of this sample space is called S here. And actually, if you do the experiment, we are now slightly going to change the experiment, we are going to ask we are going to ask the same question to two people randomly chosen. In this case, actually, the first person may say yes, the second person may say yes. So this is one possible outcome. So now note that the outcome now is not a single person, because the experiment itself is going to be the result of two people being asked. So the outcome will consist of two results. So yes, yes is one result, yes, no is another result, no, yes, and no, no are two different results. So therefore, as a summary, there are four different members of this sample space. Of course, there may be other answers which may mildly, moderately knowing, but I have excluded them, of course. Okay, so there is one important point here. Note that sample space may change in a random experiment on whether the samples are selected with replacement or without replacement. What do I mean by that? So depending on the type of the experiment or the procedure of the experiment, the sample space of almost the same experiment may change. What do I mean by that? For instance, let's slightly change the random experiment. Let's say that there is one blue, one red ball in a container, and we randomly choose 2 balls from this container. So if we do this, if we perform this experiment with replacement, that means when I take one ball, let's say I take a blue out, then after recording that it is blue, I put it back here. Then from blue and red, we are going to take another ball. So it is possible that blue and blue may be an outcome, right? From this perspective, with replacement, you can have blue, blue, red, red, blue, red, red, blue. So there are going to be 4 outcomes from this. There are going to be 4 outcomes which comprise this sample space. When it comes to an experiment with replacement, once we take, let's say, blue, then I don't put it back. The second one is going to be necessarily red. So if I do the same thing here, and the other possibility, if I take red, the other one is going to be, of course, blue. No other option is possible. So the sample space is going to be blue, red, and blue. So in determining the sample space of a random experiment, the details of the random experiment carries utmost importance. So, and one of the most important thing is whether we conduct the experiment with replacement or without replacement. So another definition, actually, as we go along, I'm going to be giving you those definitions in small steps so that it's not going to be too much boring. I give all the definitions once and for all. A sample space, what I mean is here, these outcomes may be discrete if it consists of a finite or countable infinite set of outcomes. For instance, here we have a finite number of outcomes, here 2 outcomes, here 4 outcomes. So these are discrete sample spaces. Well, if for a finite or countably infinite set of outcomes, still is going to be discrete. You may say, okay, just give me a natural number, right? It may be any natural number. It's going to be infinite, but it's going to be countably infinite. Therefore, it's going to be discrete. So you may think that this seems to include all the possibilities. Actually, no. For instance, real numbers are not countably infinite. So they are actually continuous. So the sample space, for instance, of which belongs to real numbers is going to be a continuous sample space. So the typical example may be temperature readings. Actually, still due to physical constraints, there may be a minimum limit because you cannot go below 0 Kelvin theoretically. And the upper temperature, things like that, there may be an upper limit. Nevertheless, still, if you consider real numbers, it is still a continuous random variable because it is an uncountable infinite. So here there is a distinction of countable and uncountable infinite. That's not that much important for this level. All right, now comes the third concept, which is event. So we are going to combine the things that we have learned up to this point, a subset of the sample space of the random experiment. So we have the random experiment here. So the random experiment here is, let's say we have an experiment here, right? This experiment may come out, may give us different results, right? And the sample space is all of these possible results. We are only interested in a subset of this sample space. This subset of sample space is called an event. This is the idea. So in heads or tails, let's say we are only interested in tails, then it's going to be the event that we are interested in is going to be tails. So for the previous example, what are the outcomes of the event? That at least one ball is blue. I'm talking about the two repetitions of two balls chosen from the, let's say, this experiment. Let me go back and show you the one with the replacement. So if this is a single, if the sample space, we are interested in the elements of the sample space, which includes at least one blue ball, which of course means it means blue, red, red, blue, blue. The ones excluding red, red, all the subsets are included in our event. Now note that there may be some extreme values of these events. Let's say the event that at least one ball is yellow, because there are only blue and red balls, and we have 4 different outcomes in our sample space. We don't have any samples which include one yellow ball. Therefore, the event that we are talking about, this one, at least one ball is yellow, is actually empty set. And at least one ball is blue or red is, which means, again, to think about the experiment, we have blue and red balls, blue, blue, red, 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 blue, blue, red. Actually, at least one of them is blue or red itself. It may be any of 4. Therefore, the event space is going to be equal to sample space. So sample space is all elements, and events or event space is a subset of these elements, but that event space may be empty set or it may be sample space. All right, now this is actually related with set theory that I'm going to be talking about in a couple of minutes, but very briefly. We can, using the operations in sets, we can come up with new events using the already defined ones. What do I mean by that? For instance, you have, let's say you have defined E1 here and E2, 2 different events. If you combine them with union operation, it means that we are interested outcomes that are contained either E1 or E2. So it may be either in this one or in this one. What do I mean by that? Let's say that E1 is, okay, we are tossing a dice, and E1 is, let's say, the outcome is going to be 1, 2, and E2 is going to be the outcome is true. Then the new event that we are interested in is, if you define it that way, now the new event is going to be any of these outcomes. And note that the sample space is going to be equal to 1, 2 to 6. So this is going to be our sample space. E1 and E2 are defined that way. This new E, let's call it E3, is equal to E1 union E2 is going to be 1, 2, and 3 in another subset of sample space. Now, intersection is, I guess you know this from set theory that you have probably learned in high school. It's going to be intersection of these 2 events. For instance, here, the intersection of these 2 events is empty set. But however, if we had only a 2 here, for instance, 2 here, then E1, E2 is going to be still equal to this one, but E1 intersection. E2 is going to be equal to 2, and call this E4. A new event can be defined by this way. And complement of an event, outcomes that are not contained E1. So actually E1 complement here is going to be equal to, what do I mean by E1 complement? It's going to be in sample space, but it's not going to be in E1. So it's going to be 1 to 6, and it's going to be 1, 2. And these are not included here. Therefore, it's going to be 3, 4 to 6. So these are the outcomes. As you can see, this is just a set theory. And you can use Venn diagram to represent sample space and events defined for random experiments. All right, so there is another definition that we pretty much use in probability: mutually exclusive events. If E1 and E2 has no intersecting elements, right? If their intersection is equal to 0, just like this one, 1, 2, okay, let's get rid of this 2 here. If this E1 and E2 are defined by this way, E1 and E2, then E1 and E2 are mutually exclusive because their intersection is equal to empty set. So, well, we're going to talk about those when it comes to real life events, but I guess you can think about, well, this tossing a dice is already a real life event, but you can think about, for instance, E1 is that it's going to rain tomorrow, and E2 is going to be, it's going to snow tomorrow. Then E1 and E2, are they mutually exclusive? Actually, they are not, because it is possible that it may both rain and snow at the same time, or maybe during different hours in the same at the same day. So they are not mutually exclusive events. So, but we can think about something like, okay, 2 hours later it's going to be night, and 2 hours later it's going to be day, right? Daylight, we may say daylight and night, it's impossible to have to both of them to occur because you need either sun, the presence of sun, or absence of sun, since it's impossible to have both of them. So therefore these two events are mutually exclusive. You can come up with those examples on your own. All right, now after having these concepts, still please note that we are not anywhere near to probability. We are just wandering around the concept of probability. We are trying to approach. So what we have done here up to this point is there are some experiments, or maybe all the experiments, that do not lead to a single answer, but potentially it may give different answers. And those answers are events, sample space of the experiment, random experiment, and we may be interested in some of these samples, and these are going to be events. Now the question is, what's going to be the size of these sample spaces or event spaces? Is it possible to determine them? Of course it's possible, as you have seen here. Let's go back. I have determined here there are 4 elements. Here there are size of the sample space is 2 here. It's very obvious, right? So here the event space, the size is equal to 3. So it's possible. But now the question is, if in some cases it may be very difficult to write all the outcomes. So are there some practical formulas for us to compute the size of the sample space and event space without having to write all of the outcomes? Yes, there is, and these are called counting techniques. So the first counting, there are going to be 3 counting techniques that I'm going to be talking about, and the important point is human mind somehow can handle these operations without thinking about them, without referring to those rules, which we may call heuristics or intuition or whatever. And I don't want you to do that. Actually, I want you to whichever operation you do related to probability, I want you to refer to each of these rules so that you realize what you are doing. So in a way, I don't want you to use your heuristics too much, but confine your operations to any of these approaches and realize what you do at each step. This is, I think, the important point to understand these concepts. Okay, the first rule, what we call is multiplication rule. It has a somewhat seemingly complicated definition, but actually it's very simple. It says that if an operation can be described as a sequence of k steps, and number of ways of completing the ith step is ni, then the total number of ways of completing operation is n1, n2, and k. These are multiplied, which can be shown in this representation. Note that just like summation operation or operator, this one is a multiplication operator. So we multiply all these different ways at each step. So let's try to understand what this says here. Without going into an example, first try to understand conceptual understanding of the definition. So we are going to have a procedure that's going to be completed in k steps. It's going to be step 1, and there's going to be another step 2, and it goes like this to step k. And once we actually did this during this step 1, this going from this point to this point, let's say it's from the 0 to the first state, or from 1 to the second state, there is not a single path, but we have all these paths, n1. And going from here to here, let's say this is not again the single path. There are n2 paths, and it goes like this until we have here nk paths. Note that they may be equal to each other, then they are going to be equal to just n, so it's going to be simple. So the whole thing is n1 times n2 times nk is going to be the total number of different ways of completing the procedure. And I think it makes pretty much sense, right? Because you can go here through this step, then once you come here, you can choose another one. Now, the very important thing here, this is a sequence of k steps. This should be k independent steps, I should have said. Now, I'm going to define independence in a couple of minutes, or maybe the next lecture, I guess. Yeah, I'm going to define it in the next lecture. But still, I think from daily life, we got an understanding of what independence is, which means actually once you come here, you don't care about which road you have taken here up to this point. You can take any other road. All right. So still, please note that this is not related with probability yet. These are just counting the number of outcomes in a random experiment. So a typical example may be a factory manufactures 3 different cars, each in 4 different colors. How many different outcomes can be realized? Now, actually, without referring to any formulation, one tends to easily think about the result as 4 times 3, and this is exactly what I don't want you to do. So what you should do is you should make the question similar, or you should convert the question to a form that is suitable with the theory. And the theory here should realize that this can be solved using a multiplication rule. So let's try to change this scenario into a form that is similar to the multiplication rule. So we have 3 different cars, which means 3 independent steps. This is the first step, and this is the second step, and this is the third step. And in this step, we produce car 1. And in the second step, which is irrespective of how we have produced car 1, this is going to be producing car 2, and this is going to be car 3. But note that this is not the only way of producing car 1. There may be other ways of producing car 1, which means 4 different colors, 1 to 4. And the same thing is also applicable for this one, and the same thing is applicable for this one. So 1 to 4, 1 to 4 here. Therefore, n1 is n2, n3 is equal to 4, and k is equal to 3. Therefore, it's going to be ni multiplied from I1 to 3, which is going to be equal to 3 times 4. Ne yapmışım burada ya ben? Okay. So let's continue with an example. Now here we have a factory which manufactures 3 cars in 4 different colors. So there are 3 different brands of cars, or I don't know, something like this. And each of these cars are produced, manufactured in 4 different colors. How many different outcomes is possible? Actually, let's say a more complete description of such question is required, and that's one of the reasons why I haven't written that much of description, because depending on that description, the question will have different answers, and I don't want you to just pick up the numbers and put them in an equation or user intuition and come up with a result. I want you to understand the details. So that's why I haven't given you all the details about the question. I want you to, let's see what is required additionally for this question to come up with a scenario and to come up with a proper result. So if the question is like, let's say we have this factory and there is a guy here, let's say the manager, who decides which of the 3 types of cars is going to be produced today. And there is another manager, or let's say the same guy. Once these 3 cars, and one of these 3 cars is chosen, then the color is again chosen by the same person. If this is the procedure, then this is going to be the result. So what do I mean by that? Let's make this procedure, liken this procedure to the theory at hand, which is the multiplication rule. So this procedure consists of 3 steps. In the first step, that manager is going to choose between 3 different cars. So this is at 0 state. This is state 1 where the car is chosen. So going from this state to this state, there are 3 different paths, which are 3 different cars. When we come to this state, we are going to have cross between along any of these 3 paths, and we are going to be produce 1 car. And once we have chosen the car, then color is going to be chosen and it's going to be painted. And for this one, we are going to have 4 different paths. So therefore, we are going to have 2 steps here, right? And after this, the first step is going to be consisting of 3 different ways, and the second step will consist of 4 different ways of completing. So the equation says that under these conditions, n1 times n2, there are going to be 12 different ways of completing the whole procedure. So this is the answer to the question if this is the whole description, which should be explicitly written down in the question. It's not, but as I said, it is for you to understand those missing parts. So with that information, the question would not have answer because it's not clear. So you may say, what other options or procedures are possible? All right, so another procedure maybe, or another description of the process could have been easily like this. Again, you are going to realize that this pretty much fits to that description. A factory manufactures 3 different cars, but actually it always, in a day, it always produces these 3 different cars, right? So therefore, we are going to have, again, the manager here of the factory. This manager cannot say that any of these choose this car today or the another one today or another one today. These 3 cars will be always, the first type is this one, this is the second one, and let's say this is the third one. They are going to be always manufactured. But for each car, manager can determine or dictate which color of that car can be used. So for this one, actually, manager says among those 4 different colors, black, blue, green, yellow, let's say, choose blue. So they are going to apply this one for blue, and for this one is the same thing, and for this one is the same thing. So in this condition, let's convert this question to the multiplication rule theory. So please note what we are trying to do. What we are trying to do is not to liken the theory to the question, but vice versa. We are trying to convert the question in a certain architecture suggested by the theory. So here we are going to have the first step is going to be from this state to this state, choosing the first car, or the first car, choosing the color of the first car. This is the manufacturing of the first car, but what we are going to choose is which color is going to be used among 4 different colors. So once this, so here the step is going to be, step 1 is going to be the car itself. So now the second car is going to be manufactured, but which color is it going to be? 4 different colors here. And the last car is going to be, again, among 4 different colors. So here K is going to be equal to 3, and N1, N2, and N3 is going to be all equal to 4. So it's going to be N1 times, which are, let's call it equal to N. So the total number of the cars that can, the total number of ways of finishing this process is going to be N cubed, which is 4 to the power 3, which is going to be 64. Now, as you can see, depending on the details of the question, the answer of course changes, and also the application of the multiplication rule also changes. Actually, there may be, and note that this description also seems to fit to that summarized question. So the details of the question is important, and I admit that there may be other possible ways of suggesting the details of the procedure, so that it's going to be both compatible with what's written here, and it's going to give a different results. So the details are important, and I also try to summarize what I want you to do. I don't want you to use your heuristics and come up with a made-up answer, a street smart solution, but apply the theory at hand. So the first method, counting method, is multiplication. As I said, it should consist of independent steps. Oh, one very important point here. Note that these choosing colors are independent each other. That's why I were able to multiply these numbers. Or once you choose a car, then choosing the color, I mean, whichever solution method, whichever question, I should have said, whichever question that we solve in both questions, we had the independence assumption. All right. Now, instead of step by step, and at each step we have N1 and 2 ways of dealing with the solution, or employing the procedure kind of question, another question that comes up pretty much often, and we need to use counting techniques to find the sample size or event sample size, is ordering of these elements. So if you have some, let's say, different elements that are distinguishable from each other, so black ball, a gray ball, a white ball, let's say, and then what you want to do is you want to order them, right, in different ways of ordering, right? This cannot be solved by, actually you can liken it to multiplication rule, but as the question gets more and more difficult, it is much more difficult and almost impossible to solve by multiplication rule. So for these questions, we have what we call permutation, and then what we call combination. In permutation, we have these distinguishable, and in a couple of minutes I'm going to talk about indistinguishable objects, but let's, for the time being, let's take distinguishable objects, so 3 distinct objects. In how many different ways we can order them? So let's say here we have 3 distinguishable objects. In this case, so here it says different elements, n factorial is the number of permutations of n, which is going to be equal to the sample size of all the possible outcomes. So for instance, if we have 1, 2, and 3, you can, these are 3 distinguishable elements. You can order them as 1, 2, 3, 1, 3, 2, and all these 6 different ways. In a way, you can make this, you can liken this to counting technique. What do I mean by that? Here among 1, 2, and 3, this consists of a 3-step procedure. In step 1, you can choose 1, 2, and 3. So there are three, so nothing is chosen. The first element is chosen. Then the second element is going to be chosen. And the last element is going to be chosen. So here we have n1 equals 3, n2 equals 2, and n3 equals 1. Different ways of crossing these paths. Therefore, the total number of different choices, different ways of passing through between these 2 points, from this first point to last point, is going to be equal to this. And this is going to be exactly equal to here n3, or actually this should be n1 and n3. I'm very sorry. This leads to the same formulation of n1 factorial. The logic is still the same, but I wanted to get used to permutation instead of using the counting rule. For this very specific case, it doesn't matter, but as the question gets much more difficult, we are going to automatically need these permutation rules. And actually, we are going to see these slight complications even at this point. Two variations on permutations, I may say. Let's say that not all elements are distinguishable. What do I mean by that? If we had actually 3 balls here or 3 numbers, it was like this. What about if we have another black ball? So you may say, what's the big deal? Now, or in this case, it's going to be 1, 1, 2, and 3. Now, note that it's going to be different than 1, 2, 3, and 4. Why? Because when you write 1, 2, they are going to be, for instance, something like this: 1, 3, 2, 4. And if I equate this one by this one, it's going to correspond to 1. And here, this is going to be, this 2 is going to be 1, and 3, and 4. Okay, now, so these two, for this distinguishable case, is going to be like this. For the indistinguishable case, it's going to be like this. Now, here is the very important point. For the distinguishable case, this one, if you just swap these, it's going to be 2, 3, 3, and 1, and 4, if you swap these. Whereas when you swap these, it's going to be again the same permutation. So here is the idea very simply. When you have indistinguishable elements, if you just omit that distinguishability criteria, if you assume that all of them are indistinguishable, some of these, actually the ones which can swap within themselves, the indistinguishable ones, will increase the counting, the sample size unnecessarily. So actually we get rid of these swapping elements. And here, when you have actually a single element here, 1 and 1 here, note that it's going to be wherever you have 1, 1, 3, 4, something like that, these two can swap. Actually, in this case, you should realize that this would be if there were no, they were all distinguishable, we would have 4 factorial different ways of ordering these elements. But note that since actually 2 of these are indistinguishable, there are going to be always 2 repetitions of those. Therefore, we are going to divide all the total number of these different ordered elements by 2 to get the result. Using the same logic, actually, for a higher number of elements, we can come up with this very simple equation. It says that n1, n2, nr is the number of distinguishable elements, which sums up to n factorial. You can use this rule to come up with that result. Right? So for instance, for this very simple example, it's going to be 3 factorial is going to be, you assume that first of all, they are all distinguishable. However, this has 2 elements, so it's going to be 2 factorial, and this is repeated once. So it's going to be 1 factorial. So it's going to be 3 times 2 over 2. There are going to be 3 actually outcomes here. Actually, if you see the permutation, if you would like to see the permutation of that group, it's going to be these 3 elements. No other outcomes is possible. And as I said, the logic comes from here. You may say, where does the permutation, the factorial comes from? Because, well, actually, when it's 2, it's not easy to see that. But when you have 3 elements, note that 3 indistinguishable elements, note that the excess number of repetitions, the excess number of outcomes will be 3 factorial, all changing, interchanging between these 3 indistinguishable elements. Okay, now the second intricacy in permutation is if a subset of R elements is selected from a set. For instance, let's think about an amino acid, a group of amino acids. Let's say there is glycine here, there is alanine here. Say there is aspartic acid, which actually I forgot the symbol, but it's, yeah, alanine, aspartic acid, and glutamate. Something like this. Maybe I should have chosen something else, but let's say that we have those 4 amino acids. They are distinguishable amino acids. Now, how can you arrange them in different orders? 4 factorial. All right, now the question is, let's say there are only 2 spaces that we can use these amino acids. Therefore, in this case, how many different orderings are, what's going to be the sample space, or how many different orderings are possible? What we do here is, here n is the number of elements. It's going to be 4 factorial divided by, and I said, let's say there are 2 spaces only. Here is the R elements are required. It's going to be 4 factorial. So it's going to be 4 times 3, it's going to be 6. So here another example, there are 3 elements. We are going to choose 2 elements here. So it's going to be 3 factorial, 3 elements here, and out of these R is going to be, note that here R is going to be R equal to 2. Now R is going to be again 2, so it's 3 minus 2 factorial, which is going to be equal to 6. Now, I'm going to talk about combination in a minute, but note that actually this rule is derived by combination. Why? Actually, you can think about this procedure as similar to multiplication rule, which consists of 2 steps. In the first step, think about like this. In the first step, out of these 4 different outcomes, or 4 different elements, we are going to choose 2 of them, or out of these n, we are going to choose 2 of them. So the different ways of choosing these 2 is going to be n r factorial. And once we choose these, we are going to be then reordering them in the first one here, the second one here, or the vice versa, like this. So it's going to be times r factorial. So if you write it that way, n factorial, n minus 1 factorial, r factorial times r factorial, these will cancel, and we end up with the second intricacy, or second the variation on permutation rule. But basically it is a combination and multiplication rule together. So now actually, without talking about combination, I'll talk about that. But for those who are watching the video and who do not know combination, you can now watch this part and then rewatch what I just talked about. Now, combination is the selection of a subset of R elements without ordering. So actually, it is similar to this one, but we don't have that additional thing here. I'm sorry, that reordering element here, that R factorial. You have 4 elements here. Out of these 4, we have only space for 2, and we do not care about the ordering. So maybe for this question, the amino acids is not a very good idea, because usually the ordering or the sequence is very much important in proteins. There may be other examples. So there may be, you may say, for instance, a black and a shaded ball and a dotted one and a white one. And we have space for only 2, and we don't care about the ordering. This not 1, 2, so the ordering is not important. So whichever those 2 is, the question is, what is the sample size of such an experiment? So out of 4, we only want 2 elements. So in this case, 4, 2. Actually, this is n choose R. It is pronounced as this way. So it's going to be 4 choose 2 is the number of combinations among 4 elements. 2 are chosen, and we do not care about the ordering. So as you can see, this is very much like this second item about permutation. The ordering is not important here in combination, whereas in here it's important. So let me try to show this, all of these stuff on an example. And let's start with, actually it's going to consist of a couple of steps. First, it's going to be very easy, then it's going to be a little bit tricky. So we have 6 balls with different numbers on them. In how many different orders can these 6 balls be chosen? So we are going to choose one ball here, then we are going to choose another ball, and the result is going to be a 6-digit number. Note that, and how many different 6-digit numbers can be obtained. And note that this is going to be simply equal to 6 factorial, because this is just permutation. You can also think about the counting rule, right? You choose one element here among 6 of these, so it's going to be 6 different paths, 5, 2, 1. But I recommend you to use this one directly, so that it's going to be easier to handle much more difficult questions. All right. Now the second question, how many different ordered ways can 4 of these 6 balls be chosen? So we are going to choose not only, we are not going to take all 6 of them, but we are going to take 4 of them, but we are going to read the resulting number. So each ordering refers to a different outcome. So it's going to be exactly this second item here. A subset of R elements is selected from a set. So here R is going to be equal to 4 and it's going to be equal to 5. So if you go back to the equations, n factorial, n minus R factorial. So it's going to be 6 factorial over n minus 4 factorial, n factorial over 2 factorial. And I hope you are comfortable with these calculations. These will cancel, and this is going to be whatever the result is going to be, something like 360. I don't know, just check the result. Now let's see how many different groups of 4 balls can be selected out of these 6 balls. Ordering is not important. Now I don't care about the resulting, the ordering of the digits. Whether a ball is chosen among these 4 is a sufficient criteria. And in this case, it's going to be combination rule, right? So it's going to be 6, choose 4. So it's going to be this element. So it's going to be 6 times 5 over 2, which is going to be 50. Up to this point, it should be simple, but please realize that I refer always to which equation I use, and I would like you to do that. Especially in exams, I would like you to write down the equation number which you use. So I don't want you to use directly this or even this one. So that I want you to show that you understand the reasoning why you use this combination. Now comes a tricky question, I may say. In how many different ways can these 6 balls be placed in 10 holes? So here is the question. We had 6 balls from 1, 2 to 6, right? And this time we have holes. I show the holes in square to show the difference between balls and holes, which are actually pretty difficult to distinguish while pronouncing. So these are our holes, and what we would like to do is we are going to place them here, 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 here. Of course, they are not going to place. We are not going to. Not all the holes will be filled, but some of them will be. So it's going to be like, for instance, one here, one example. It's going to be, let's say, empty. So I put the ball here, and let's say this is 6 is here, and 5 is here, and this is going to be empty, and it goes like this. And let's say 2 is here. So this is going to be one configuration. And like these configurations, how many of these configurations or the outcomes are possible? How can we handle this question? For those who are watching this for the first time, please stop the video here and try to solve on your own. using the equations we have come up with. Now, actually, there may be different solutions. Now, one of them will be, let me get rid of these. So I'm going to be talking about two different methods. There may be more. I define a two-step procedure. So I'm going to be using the multiplication rule. In the first step, I'm going to be choosing, now this is the interesting thing, I'm going to be choosing only the wholes. So among these wholes from 1 to 10, right? I'm going to be choosing 6 of those. And note that the ordering here is not going to be important. Whether I have chosen that whole or not is sufficient. So in this first step, it's going to be 10, choose 6 different ways of choosing these wholes. With ordering is not important. And in the second step, note that since I have chosen 6 of those and I have 6 balls, I'm going to put them in ordered manner. Therefore, now we are going to have permutation 6 factorial. And since this is a two-step procedure and the first step consists of that much way of completing the first step and the second step is this one, so it's going to be n1. It's going to be n1 times n2, which is going to be 10 factorial 6, 4 times these will cancel, and it's going to be 6, whatever the result is going to be. I think it's going to be, no, I haven't written the results in my notes. Okay, so just write it that way. So this is the first method. The second method is, let me call this method 1. The second method is a bit more fancy, I may say. What I do is, well, actually, you can come up with those kind of creative also answers. Once you grasp the fundamental roles of these methods and assumptions and the methods I've talked about. Anyway, so let's assume that we have 4 virtual balls. What do I mean by that? We have 1, 2, 6. These are real balls, and I add 4 virtual walls, and I call them 0. Now here is the interesting. So in reality, they are not here, but I just introduce them for the sake of making the question easier. Now I have 6 real balls and 4 virtual balls. Now I just forget about the holes because now these 4 and 6 correspond to 10 holes. What I'm only interested in is how to arrange these 10 balls. So it's going to be 10 factorial. However, note that actually these 4 are repeated. So they are indistinguishable elements. So if you go back to this part, this one here, it was about distinguishable and indistinguishable elements. So therefore, I am going to multiply by 4 factorial. And other one, these 6 are, they're just 1 factorial because I have 6 distinguishable elements. 6 distinguishable, and these are indistinguishable elements. Therefore, when you use the equation, you come up with the same answer. And these are the ways I can solve this question. If you have any other methods, but not just heuristic method. Even if you come up with heuristic, try to prove it using one of these methods I talked about. You can come up with the results. Okay, that's all